Welcome to another online lesson for a Math 513. Today's lesson is about the residue theorem. Here's the theorem. Suppose that f is analytic in an open set U, and I indicated that in pink here. U has this nice hole over here, except for isolated singularities. And so the isolated singularities, I marked those in green in this picture. Let E be the singular set of f. So all the green stuff, that's E. So that's all the singularities of f. And sigma is a cycle in U that doesn't go through any of the singularities. So my cycle sigma is in blue right here. And we're assuming that the cycle is homologous to 0 in U. That means the winding number is 0 for every z that's not in U. So anything that's in this pink blob or outside of U, the cycle can't wind around. The claim is then that the integral of f over the cycle sigma is 2 pi I times the sum of the residues multiplied by the winding number of the cycle with respect to z. So we only have to look at those z's that are within the cycle, so around which the cycle winds, and for those we calculate the residue, and we add all those numbers up. So in this particular picture, that would be this point right here, and this point, and let's see what else. These two, I think the cycle winds around these 2 points, but none of the other points actually are affected because their winding number is 0. Okay, so let's see how we can prove this theorem. The proof is in 2 parts. We'll first show that the set of all z's in our singular set for which the winding number is non-zero, so those that are part of that sum we just saw, that set is actually finite. And so the sum is actually a finite sum, so we don't have to worry about convergence or anything like that. The proof is by contradiction, so suppose not. So then we have infinitely many distinct zk's, all of them in the singular set E, and the winding number is non-zero for all of those zk's. So in particular, because the winding number is non-zero for all of the k's, all of the zk's cannot be contained in the unbounded component of c minus sigma. Because in the unbounded component, the winding number is 0. So that means the sequence zk is actually bounded. And a bounded sequence in the complex plane has a subsequence that converges. And so we might just as well assume that we chose that subsequence to begin with. And so we can assume by passing to a subsequence that the sequence zk converges. And I'll call the limit z star. Now where is this point z star? All these zk's are part of the singular set, and that means they're all discrete. E, the singular set, is discrete. What does it mean to be discrete? That means that set does not have an accumulation point within E. So any convergent sequence has to converge to something that's not in E. Because if the point was in E, then it would be an accumulation point which would violate discreteness. And so this means that this point z star, the limit of the sequence zk, is not in E. So if it's not in E, where is it? It certainly can't be in U and not in E at the same time, because then the function would be analytic, but analytic would mean it's an analytic in the whole neighborhood around the point, but all the zk's are in that neighborhood, and the function's not analytic at the zk's. And so that means that the z star point has to be contained in the complement of U. But the complement of U is part of the unbounded component of c minus the trace of my cycle. And that unbounded component is open. And so I can find a whole little neighborhood around z star such that the ball of radius r centered at z star is entirely contained in the unbounded component. Again, the unbounded component is open. But that means, you know, remember these zk's, they are converging to z star. And so eventually they have to be in this little neighborhood around z star. And so eventually zk has to be contained in the unbounded component. So for k large enough. But that means that for these zk's, we have that their winding number is 0, because that's what happens in the unbounded component. But we assumed that all these zk's are points for which the winding number is non-zero. And so that's a contradiction. And so this contradiction implies that indeed the set of all those points in the singular set for which the winding number is non-zero is in fact finite. Next, let's pick those finitely many points. So let zeta 1, zeta 2 through zeta p be those points in the singular set E for which the winding number of the cycle is non-zero. And then let V be U minus the singular set, but with those zetas added back in. So let me draw a picture for you. So remember our set U was something like this, and it had this hole in it. And then we had all these singular points in there. No, those were green, right? We had all these singular points. And I even had tried to draw a sequence that converges here. There you go. And then we had our cycle. And, you know, I don't really remember how I drew it last time, but it was something like this, maybe. It's a little different than it was. Oh, and then I had another part to it, which means I better get my 2 points back in there. All right. And then I have some other singular points. So E is all the green stuff. This is U, and sigma is my cycle. Now we're going to let V be the set U, the pink stuff, minus all the green points, minus the singular points, but we're adding in the special singular points for which the winding number is non-zero. So those are these points here. Those are the points for which the winding number is non-zero. So those are added back into U. So V is U minus the green stuff, but with the orange stuff added back in. So V is equal to U minus the green stuff, but then with the orange stuff added back in. Okay? So what does that mean? That means the cycle sigma is homologous to 0 in V. So even though we took these green points out, since the cycle doesn't wind around the green points, I might just as well take him out of U. So in my new set V, doesn't have all these green singularities anymore because they're gone. They're not part of the set. I don't have to worry about them. The function f, and I look at it in V, the only singular points of it are the orange points, those that the cycle winds around. The other ones are not of concern anymore because the cycle doesn't wind around them. So my function f is analytic in V, except for isolated singularities at zeta 1 through zeta p. So I'm going to have to erase this picture. Oh, great, I'm going to erase my writing as well if I erase this picture. Oh, well. So let sk be the singular part of f at zeta k. So these zetas are the only singular points of f in V. So sk is analytic in C except at zeta k, because it's the singular part, only the Laurent series part. And f minus sk, so if I if I subtract out the singular part of f, then f minus sk has a removable singularity at zeta k. So if I take the function g, which is f, and I subtract from it all of the singular parts, so s1, s2 through sp, then this new function g is analytic in V and has removable singularities at all these points zeta, around which the curve points. But if they're removable, we can fill them in. And so, there's some number that we can use to find g at each of those points. And then the new function g with these points filled in has no singularities and is therefore analytic in V. So g is now, we can assume this function g is an analytic function. So that means if I integrate this analytic function over a cycle that is homologous to 0 in V, remember sigma was homologous to 0 in V, and g is analytic in V, that means I get 0 by the Cauchy theorem. But g is really f minus all these singular parts. So instead of writing g, I can write f, integral over f, minus the integral over all these singular parts. In other words, the integral over f, that's what I'm really interested in, is equal to the sum over the integrals over the singular parts at these points zeta 1 through zeta p. So what does the singular part really look like? Remember, the singular part of f, and suppose it's at a point zeta 0 that belongs to the singular set, is a sum over negative powers of z minus zeta 0. So it's the sum, n from 1 to infinity, of some coefficients a minus n times z minus zeta 0 to the negative n. And the singular part by itself converges normally in c minus zeta 0. And therefore, in particular, the convergence must be uniform on the trace of sigma, which is a compact set in the complement of the singular point. And so therefore, when we integrate the singular part over the curve sigma, we can interchange the summation and the integration. And so this becomes the sum over the a minus n times the integral over sigma 1 over z minus zeta 0 to the n. What are these integrals? Well, for every n except for n equals 1, we have an antiderivative. Only for n equals 1 do I not have an antiderivative everywhere in the complement of zeta 0, and that's the one point where the integral is not going to vanish, and in fact the integral is exactly 2 pi I times the winding number of the cycle around zeta 0. So therefore, putting this all together, remember f was the sum of the integrals over the singular parts, but an integral of a singular part gives you the coefficient a minus 1, which comes from the sum, times 2 pi I times the winding number, and a minus 1 is exactly the residue. So this a minus 1 here, that's the residue of f at the point zeta 0. So in general, I get the sum over the residues times 2 pi I times the winding number, and that's exactly what I wanted to show. It's a finite sum, but we might just as well write it as a sum over all points in the singular set because the winding number is 0 for all but finitely many points in that singular set. And that is the proof of this theorem. So let's look at some examples. So let's suppose we wanted to find the integral over this bizarrely drawn curve gamma of the function z over e to the z minus 1. So gamma is defined on an interval from a to b into c, and is given by this picture. I don't have a formula for it. So what is the function like that we're integrating? The function is f of z equals z divided by e to the z minus 1. And where does that have singularities? Well, it has singularities whenever the denominator is 0. And so that is whenever e to the z is equal to 1. So it has singularities at the points 0, 2 pi I, 4 pi I, 6 pi I. So in general, it's 2 pi I k, where k is an integer. We are interested in those singularities for which the winding number is non-zero. So we have the winding number of this curve gamma around the singularities zk, where these are my zk's right here, is equal to 0 for all k's that are not equal to either 0, 1, or minus 1. So only 0, 1, and minus 1 are those around which the curve actually winds. So we only need to consider the points minus 2 pi I, 0, and 2 pi I. So in other words, we need to look at the integral. It's by the residue theorem, it's going to be equal to 2 pi I times the sum of the residues times the winding numbers at these 3 points. So we're going to need the winding number of gamma around minus 2 pi I times the residue of f at minus 2 pi I. Then we're going to have to add to that the winding number of gamma around 0 times the residue at 0. And finally, the winding number of gamma around 2 pi I times the residue of f at 0. So let's find these winding numbers. How often does gamma wind around negative 2 pi I? Well, negative 2 pi I has this extra loop, so the winding number is actually 2. Whereas for the other 2 points, the winding number is simply 1. And so altogether we get, for the integral to be 2 pi I times 2 times the residue of f at minus 2 pi I, and 1 times the residue of f at the other 2 points. So we're going to have to find these residues at these 3 points, and then we're done. Here again what we just found. We have 2 times the residue of f at minus 2 pi I and the residue of f at 0 and at 2 pi I. And we have to multiply the whole thing by 2 pi I, and that'll give us the value of the integral. So how do we find these residues? Well, let's start with 0. Well, 0 is pretty special. 0 is actually a removable singularity. So why is that? Well, the numerator is 0 and the denominator is 0, and both have a single 0. It's a removable singularity, and we can find that by looking at the limit as z goes to 0 of f of z. So z over e to the z minus 1. And by L'Hopital's rule, that is the same thing as the limit as z goes to 0 of 1 over e to the z, and that is 1 over e to the 0, and so that is just equal to 1. So it's a removable singularity, and that means that the residue, which is the a minus 1 coefficient, is not there. And so the residue is equal to 0. So this thing right here is equal to 0. Now let's look at the residues at 2 pi I and minus 2 pi. Both of these are simple poles. So first we have to prove that they're simple poles, and then we can use our formulas. 2 pi I and minus 2 pi I are simple poles. So we need to look at the limit, start with 2 pi I, as z approaches 2 pi I of z over e to the z minus 1, that's my function f, times z minus 2 pi I. If we're dealing with a simple pole, then this limit exists, and vice versa. Well, the limit of z as z approaches 2 pi I is simply 2 pi I, so that doesn't really affect anything. So we might just as well pull that outside of the limit. So 2 pi I times the limit as z approaches 2 pi I of z minus 2 pi I divided by e to the z minus 1. And again, by L'Hopital's rule, this is equal to 2 pi I times the limit as z approaches 2 pi I of 1 over e to the z. And 1 over e to the 2 pi I is simply equal to 1 times 2 pi I, that gives you 2 pi I. So therefore, at 2 pi I find that the residue of f is equal to the limit as z approaches 2 pi I of, this is our formula, z minus 2 pi I times f of z, and that's the limit we just calculated, so that's 2 pi I. And similarly, I'm not going to do the whole calculation, well, we find that the residue of f at minus 2 pi I is the exact same thing, same kind of calculation, so it's the limit as z approaches minus 2 pi I of z minus minus, so z plus 2 pi I f of z, and so that equals minus 2 pi I. So I found this residue right here to equal 2 pi I, and this one to equal minus 2 pi I. And so now I can add it all up, and I find that my integral over gamma f of z dz is equal to the 2 pi I from the front, and that gets multiplied with 2 pi I plus 2 times 2 pi I and plus nothing. Plus 2 times minus 2 pi I, so this was actually a minus right here. So I have 2 pi I and times 2 pi I minus 4 pi I. So altogether I have minus 4 pi squared I squared, and that equals 4 pi squared. So the value of my integral is 4 pi squared. So that's the residue theorem and an example of it. And next we'll discuss a consequence of the residue theorem, which is called the argument principle.